This video focuses on the target. I can explain how the dual nature of electrons supports the quantum mechanical model by allowing electrons to move as waves and particles. To be honest with you, this is a complicated target. There's a lot going on here, but if you just focus it on the core, we're talking about how in order for the quantum model to exist, electrons have to be both waves and particles. So essentially, it's explaining why it is that the electron as a particle doesn't support the quantum model alone, and the electron as a wave does not support the quantum model alone. So let's remember kind of where we're at. The Bohr model put electrons in concentric circles, saying that they would jump up and down between these rings in order to create those absorption spectrums. The problem with his model is the physics. Okay, if you actually allowed electrons or proposed that electrons were moving in a circle around a nucleus, the physics doesn't work. There's no reason for them to stay in their path. They should be attracted to the nucleus, and they don't have any kind of like gravitational force keeping them apart based on their size. The other problem is something called the uncertainty principle, which we're going to talk about here. And then another problem was, based on Bohr's model, he did all of his proposing of the energies based on hydrogen, and he has a whole bunch of math behind it to support what the energy levels are. But then when they looked at helium, which is the next element that now has 2 electrons instead of 1, all of the math falls apart. So that first energy level is not always in the same spot for every atom, it seemed, and the second energy level as well. So this model was very poor at predicting any kind of actual numeric or mathematical information about the energies. Before Bohr, Albert Einstein was doing some experimentation, and he came up with something called the photoelectric effect. Essentially, he bombarded sheets of metal with light, and he found only certain light allowed electrons to be released from or ejected from the material. So if he shone like red light on the material, maybe nothing would happen, but then if he shone blue light on the material, all of a sudden electrons would be emitted from the material. So he came up with something called the photoelectric effect, which was essentially the idea that you need to hit the surface with a certain amount of energy to get things to come off. So again, really come up with that idea of the photon, that little packet of energy necessary to get things to move. So the idea that energies are not just a smear where like a whole bunch of different things are all in one location, but that they're actually like distinct parts. So this was the idea that light, which we've always thought of as a wave, had actually some like particulate nature to it that we would name a photon. So this is the first introduction of the idea of like, well, is it a wave or is it a particle? Since the wave nature did not explain why electrons would be emitted only sometimes. There was another experiment done as well called the double slit experiment. We did this in class where particles, electrons, which are particles, started behaving like waves when going through 2 slits. So Einstein's experimentation with the photoelectric effect kind of introduced the idea that light, which has always been considered a wave, was acting like a particle. And then the double slit experiment introduced the concept that the electron, which is a particle, tended to act like a wave also. So we're finding here in terms of being able to use our current physics models to predict behavior of electrons, we didn't know what model to use because the wave model is different than the particle model, yet both seem to be applying here. The other thing that went into using both the wave and the particle model for the electron is Heisenberg's uncertainty principle, which I mentioned. And it's the idea that when he tried to physically find the electron and both map its trajectory, so where it was headed, as well as map where it is, he couldn't do both. Okay, so he was having a hard time predicting where it was headed in terms of like its velocity as well as its location. So if he was like, oh, it should move in this location and be here, he was finding he could either figure out where it was going or figure out where it was, but not both. So we kind of walked into this world of probabilities. Okay, and it wasn't like that the electron was like way off. It's just that a lot of his models, he was only to predict maybe like 95% of the time, both velocity and position. Okay, so all of the math behind probability and statistics started rolling into the model of the electron. So in the end, how were both waves and particles necessary to make the model? Well, the quantum model, or the model that Schrodinger helped develop, was a model based on probabilities, the probability or the tendency to finding electrons. And the way their probabilities were defined was based on a wave function. So they used a mathematical equation saying that electrons were moving as waves to map those probabilities. And those probabilities are where the electron was found about 95% of the time. Now, as soon as you pinpoint an electron within those areas of probability, it does present itself as a particle in space, which is kind of how you combine both ideas. But essentially, you can't have an area of probability without acknowledging that it's a wave, because those areas were defined based on it being a wave. But you can't have a lot of like the bonding and other properties of the atom without saying that the electron is like a particle. So we have both of these ideas overlapping in the concept of an orbital, which is an area of probability where electrons tend to reside. The probabilities are based on a wave function, but the electrons are behaving like particles within that area. That's it for this concept. Have a nice night.